So, good morning everybody and welcome to the Celsius talk in May. We see that we are some 15 participants to this meeting and we are very happy to have you all here. Welcome. Today's webinar will focus on local energy markets and especially on fossil-free local energy markets. We will present the EU project FED, a unique local market and trading platform for electricity, district heating and cooling. The test bed is under development for time being in the center of Gothenburg at the CHALMERS campus area, Johannesburg. We have an agenda for the meeting today. We will start with an introduction of the FED project. It will be followed by a deeper presentation of the market and trading platform that is under development. And finally, we are happy to take your questions and have a discussion around those. My name is Irene Svensson and I am responsible for international relations at Johannesburg Science Park in Gothenburg. I am also the project coordinator for this project and I will act as the moderator today. 3 speakers will participate during our session to cover the different parts of the project. But before I leave the floor to the first speaker, I will quickly set the picture of the FED project. And FED, it stands for Fossil-Free Energy Districts. And the project is co-financed by European Regional Development Fund, which is within the program of Urban Innovative Actions Initiative, and that is a new European Commission initiative for cities to test new solutions, meeting different kinds of urban challenges. The City of Gothenburg was awarded the project in November 2016, and that was in great competition with some 400 applicants. 3 energy projects were selected among the 18 winners. The FED project will run for 3 years. It started in November 2016 and will end in October 2019. And the total budget is 5.8 million euros. And we are now halfway in the project. So, I now would like to introduce the first speaker today, and that is Claes Somansson. Claes is responsible for the focus area energy at Johannesburg Science Park. Claes is also the deputy project coordinator and responsible for technique and quality in the project. So Claes will give us an overview of the whole project. So Claes, please, the floor is yours.
Thank you, Irene. I will start to speak a little bit of the background of this project from this picture. And of course, the background, it depends very much on which of the partners you ask. But here today, it could be very interesting to speak of the background from a Celsius perspective. Actually, in Celsius, perhaps you remember because you were all involved in one way or another. But one of the demos in Gothenburg in Celsius was about how to use the thermal inertia of the buildings as an energy storage to mainly to focus on how to avoid fossil peaks, to avoid to start oil burners and things like that in peak hours in the district heating network. And this project was also in a way a bit of a start of working with smart grids in Gothenburg, but not on electricity as common is thought of, but more on a district heating level. The interaction between the customers and the district heating system is quite similar to when you have an interaction on the electrical side using, let's say, a battery instead. So this was a project, and I can also remember it quite well because at that moment I was an R&D strategist at Gothenburg Energy, the utility company of Gothenburg. Another project we also looked into, it was not a Celsius demo, but it was how to integrate other local production, small scale, in the district heating network, such as heat pumps. There are quite a lot of air water heat pumps and also thermal geothermal heat pumps. And then you come to another interesting aspect of demand side management, where actually if you have a heat pump, a local heat pump in house in the district heating system, how can you operate that in the best way? Let's say if there's a lot of wind available, cheap electricity, then it's perhaps beneficial to use the heat pump. Or when it's not, then it's perhaps more beneficial to use the waste heat or the bioenergy from the bio-CHP plants in the district heating network, and in that way to use the resources in the most efficient way. And this was a little, let's say, spark and an interest to see, okay, if we want to proceed with all these kind of interaction, how to integrate all kinds actually of small scale production that interferes both with the electrical system and the district heating system, and also the district cooling system. How can we work with that? What kind of platform, if you speak of an ICT terms, is useful here, and what is the cost and what is the benefit in each case? Because at that moment you want to proceed from looking at a separate solution to see if you can find a solution that can actually in a way cover all of it. The FED project is quite much about that. Here's one overall pictures what's it about. Irene mentioned that we focus to develop and to demonstrate a local marketplace for electricity, heating and cooling, to see if we can have a common market for these three utilities. If we had more gas in Gothenburg interacting with the system, we could of course include gas as one other utility. But in this area, we do not use much gas for heating or cooling purposes. The project has an aim to optimize or to use all kinds of flexibility in the best way to help the grids and to decrease the, of course, the fossil fuel, the use of fossil fuels, and we have targets on to reduce the fossil fuel peaks in the grid, so to speak. I mean, similar to the Celsius demo, but we want to also to look how we can use this system to avoid fossil peaks, both in the electrical system, but also in the other utility systems. And we also have a target to use the energy as efficient as possible to reduce the primary energy output for this. I will come back a little bit more on details. FED is financed by the EU program Urban Innovative Actions. It was the first call in this that we applied, and for the things we wanted to do here, we had quite an ongoing discussion between the campus area of in Johannesburg. It's the Technical University of CHALMERS, one of the larger in Sweden. And in this area where also Johannesburg Science Park is situated, there had been an ongoing discussion for many years to use the area as a test bed, to both from the real estate owner's perspective to give their infrastructure in a way to the researchers to see how they can use it in their projects. And there are quite a good advantage here, because at the university area, that is perhaps something like 15,000 end users, students and people working in the area and so on. They have their own electrical grid, and they have their own district heating grid and also their own district cooling grid. So the infrastructure is quite similar to a city in miniature. And from the urban innovative action, they wanted to really to focus on, besides the Horizon 2020 projects, let's say that you have several demos in many countries. Here they wanted to focus on one big demo in one city. So FED is only in Gothenburg in that sense. We are not working together with other demos in other cities. So the whole budget is to create one demo and to evaluate it and to share the knowledge in Gothenburg. And we have about 5.8 million euros. So this really gives us a very good opportunity to create an urban lab in the city in this topic that we are very glad for. There's 9 partners in the project. It's the City of Gothenburg that owns the project. It's they who represent the application. It's only cities that can apply at that moment, at least. Johannesburg Science Park, mine and Irene's organization. We are quite a small organization. We're owned by the City of Gothenburg and the University of CHALMERS, together with several industrial owners, and we have the responsibility to coordinate or to project manage, but also the work package for communication. Akademiska Hus and Chalmers Fastigheter are the real estate owner, or they have all the premises in the area. So, and they also do some investments to advance here to try to create an area that's even more like the future energy system, with a lot of local production and storages. So they are investing also in a lot in solar PVs, let's say, and some new heat pumps and some other infrastructures and energy storages here to make the demo even more interesting. We have Chalmers, the University of Technology, and they work, I think the core thing is to build a model of the area that you can calculate and to see what are the best investments and how can we do the operation, and also how we can look if we scale this up to the city level or if we try to use it in another part of the city. We have Ericsson, as Joachim will speak more of later, that actually will create the ICT platform that is used in this project, and they use their knowledge from other projects and their existing building systems, etc. Business Region Gothenburg is an organization within the City of Gothenburg, and their role here is to help with the communication and to share the information from the project, but also to look at possibilities for replication. And RISE, the Research Institutes of Sweden, are involved in almost every part. Actually, all partners are involved in almost every part. It's a very integrated approach here. And RISE, as Magnus will speak, they, for example, have done much of the design and thoughts about the market solution here. And Gothenburg Energy, the utility company, of course, they're very interested in their part because this local market is connected to the overlying markets in the city, the district heating and the district cooling, and also the electrical system. This is a picture, speaking of the purpose and how it connects to the programming within EU as well. It's a very large focus on the energy transition in EU, with the goals to replace coal and nuclear and such non-renewable production to wind and solar mainly, and of course the aspects of more volatile electrical production, and also the small scale aspects. The security of supply is of course also a topic. I think they address this topic much closer. It's a project in its own actually to look into this into deep. But the aspect you can see here is both that you have a more decentralized system, and which means that you have you reduce the vulnerability for if you compare to having a system relying on just a few very large nuclear plants, let's say, like in Sweden. Or you can also look at it as the aspect that when you're more and more into the Internet of Things and to open up the data from the systems, the vulnerability that might appear at that moment as well is also a security of supply question, I think. The smartness, of course, it's this is a system where you share information in both directions between producers and consumers and back and forth, but you also let the energy flow in back and forth. The district heating system, you can be you can be a producer and a consumer at the same time in all the three utilities in a way here. Renewable production is also one thing. It's one thing to highlight from a Swedish perspective, actually, because it's a little bit not to say odd, but to have a project on fossil-free energy district in Sweden, because the Swedish energy system is almost already fossil-free compared to many others in Sweden, because most of the electricity comes from hydro plants or nuclear plants. But the nuclear plants in Sweden are old and they're about to be replaced in the nearest years. 2 more reactors will be closed in 2019 and 2020, and it's quite expensive to replace them with new ones. So the plan is, and it's a goal in Sweden, to within 2040 have a renewable production of electricity. And that's a little bit why this project in Sweden can help to see, okay, how can we arrange the alternative from today's system with a lot of nuclear. And the last one on this picture is, of course, sustainable business models. And this is a little bit why we want to look at it as a market, because then we can analyze each market participant and see what is the benefit, what is the value for each market participant, and to describe the business models and the relationships from this perspective. I will just short mention the marketplace here and the detailed solution, because Magnus will speak more of this. But let's say that we divide, this is a picture of the campus area or an illustration. We divide it into local market participants, and it can be producers of all kinds. We have solar PVs, but it can also be on heat, like heat pumps or bio-CHP plants, and or district cooling plants. And we have, of course, consumers. Some of the house did more consume, and we have producers and or prosumers, actually, where you combine that you have a production facility together with consumption and also energy storage. And I think in total at the moment we are now looking at something like 45 different market participants in the area that will be connected to the marketplace of various kinds. We have the 3 local grids, as I mentioned, on district heating, district cooling, and electricity. And we also have the external production in the district heating system of Gothenburg that is connected to the area. I think it's approximately 30 to 40 different production facilities in the large system as well, with waste heat as a base, and then heat from waste incineration, and also bio-CHP, bio-boilers. We have natural gas CHP and natural gas boilers in the system. So, and also large heat pumps from sewage water. So it's quite a complex system. And in this, one unique thing that we haven't tried that in Gothenburg is that we will create an hourly based price on district heating for this system. So we will update the price each hour with a prognosis from Gothenburg Energy here. And in the same way we can do with district cooling. And electricity, we use the hourly price from the Nord Pool spot market already existing. And on the grid side, we can actually provide services both to the local grids and to the city grids, and also on the electrical side to the national grid of Sweden as well. This is more a picture with the same information approximately, that's saying what kind of local market participants that we have, and you can see it in a different way. we give you that in the protocol. My last thing is to mention the milestones that we have. We started in November 2016. The first half year approximately was to set the design, to do the planning of the project. It's quite a lot to synchronize these quite huge amount of man hours that we put into this project. So we had a plan with the design of the basic design of the marketplace in June 2017, together with the plan for the investment we were supposed to do. In December, we had the first version of the trading system within the House of Ericsson that they tried to develop and to transform this design into code. This has been further developed and will be more fully developed in the summer of 2018. And in the summer now, we will also do the first test of the system with a few market participants to see the end-to-end test, how it works. And then we will continue during the year to add more market participants to the system with the aim to have all investments and all in operation in December this year. And then all of 2019, or at least till in October 2019, we will write our final report and have the evaluation finished. And in parallel now, we will work on how we can replicate this to see the barriers there can be within or from legal aspects or from social aspects or from economical aspects. What's the cost to replicate, and do we mean to replicate all of it, or do we mean to just replicate parts of it? Shall we replicate the thing to another similar area, or should we replicate it to the city as a whole to be operated from a utility company instead? You can do quite a lot with this, and we will work with this all this year as well to investigate this further. And in that way, we were interested, if someone listening at the moment is interesting to share knowledge from your city, or to take a look if, okay, these aspects that we investigate here, how can they be perhaps used in the system? It's something that we could be interested to cooperate as well. And by that, I say thank you, and we'll come back with questions later.
Thank you very much. I'm coming back to the picture. Thank you, Claes, very much for this very good presentation that give us a very good picture of the project and where we are and what we are going. So now I would like to introduce the next speaker, and that is Magnus Brolin. Magnus is working with energy markets and systems at RISE, Research Institutes of Sweden. And Magnus will give us a deeper picture of the marketplace, which is, as we have heard from Claes, a very vital part of the project. So Magnus, please, the floor is yours.
Thank you very much. And let's see now, I will make sure that you can see my screen. Oh. I don't know if you see my screen or if you see my preview. Can you say something about that, Irene? Which one do you see?
I see your first picture, Fed market design from May 2018, with your name on.
Okay, perfect. Let me run it from here. Okay, thank you very much for the introduction, Irene. And my name is Magnus Brolin. I'm working at RISE as a R&D portfolio manager in energy systems and markets. I also have a role as a senior researcher in electricity markets and trading, and it's in that role that I'm here presenting the Fed market. RISE has been involved in several parts of the project, as Irene and Claes has previously described, both in terms of monitoring and of the progress of the project and measurements and stuff like that, but also on the market design and architecture of the marketplace. And that's what I will discuss or present here. Now I will go a little bit more into detail than what Claes did, but I will not give you the nitty-gritty details. So if you have any questions about that, we can take that later on. Okay, so this is a similar picture as Claes previously showed you. I just wanted to point out that the local market is an integrated market of the different energy carrier systems, heating, electricity, and cooling, but also it has a, you can say, a gateway to the external production and the external markets and systems. I think that's important to state that and to point that out, because many of these systems might not be self-sufficient at all times, so import and export might be are important for also the local system. So the marketplace needs to facilitate that kind of exchange, not only within the system as it is, but also to the external system and market. There are a number of aims. I think Claes stated a little bit about the overall objectives and aims of the Fed project, and if I remember correctly, you said it was one of the aims was to lower peaks, especially fossil peaks, and in that makes raises a need for some kind of coordination of the resources being available in the local system, meaning that you need to when do you need to use your storage in order to avoid fossil peaks? How can you use available existing production that might be renewable in an efficient way, and so on. So some kind of coordination function of the local resources together with the external system and market through exchange of energy is an important aspect, and one of the roles of the local market is to facilitate that and to make that actually happen. Now, it's also important to lower the threshold for local actors that might not have the, you could say, extensive knowledge on how electricity markets or energy markets work. So you need to somehow lower the threshold for those actors to become active market participants. And one way of doing that is make sure that the marketplace offers the right functionality in order to, for example, execute flexibility in the system, to use demand response and such aspects as Claes previously discussed. That is also an important aim of the marketplace. It's also a platform for offering system services. System services is you could say a term for services targeting specific technical issues or needs from a technical perspective of the different systems. And I will come back to that a little bit later, but that's also an important aspect of the marketplace. Another aim is also to enhance integration of these different energy carrier systems, such as heating, cooling, electricity. And the reason for that is that you can exploit both synergies, but also to make flexibility available by, for example, switching between electricity and heating for heating purposes in buildings, for example. So this integration of energy carriers is also a very important aspect of the marketplace. Now, this coordination function that I mentioned before can be achieved by different means. One is you can say an extreme option one to the far left here. That is actually having a technical system that takes control of all the local energy resources that you have in the system, buildings, building control systems, energy storages, heat storages, or batteries, etc. So that is a rather, you can say, technical view on how you can operate the system, giving all the control to a central control system. Now, from a technical perspective, that might have the, you can say, largest potential to actually achieve the efficient use of available resources. It, however, lacks the you can say the potential for application. Because it needs that all the actors being within the system are willing to give the control to the central system, what might not always be the case. So it might lack some of the replication possibilities that other systems might have. And to the far right, we have the extreme option number 2, and that is kind of facilitating peer-to-peer transactions between the actors within the system. Now, that is not having a central unit at all, which means that the coordination might be less efficient. that gives it puts a lot of, you can say, responsibility on the individual actors in the system and their knowledge and their possibilities to actually understand the system well in order to execute their decisions on how to operate their physical assets in an optimal way. So that might not lead to a very efficient coordination, and therefore, to combine these two, the Fed system is somewhere in the middle of these two. It is a market-oriented system in a way that you can choose as an actor to be how involved you will be in the market. But it also has a matching of supply and demand, meaning that you can have an efficient coordination by running through this market as an actor. So it's somewhere in between these two worlds, maybe a slight orientation towards option 2, but still somewhere in between these two extreme options. So what is it? Well, it's basically, you can view it as a hub for exchange and trading between actors and partners within the system, as well as trading with the external system and market. It has an energy demand and supply matching function. It's important because that is what leads to an efficient use of resources. It's integrating the different energy carriers, meaning that we will have one marketplace, not 3 marketplaces, one for each energy carrier, but rather having these in line with each other and a simultaneous trading of these 3 different energy carrier systems. It defines transactions. That is what comes out from the marketplace, is a number of transactions to take place, and you can say a dispatch on the system. It has an energy exchange and system services through 2 different marketplaces, and the reason for this is that they have quite different characteristics. So we have an energy market and a system service market. If you're looking at, for example, the closest orientation or closest, you can say, other market that has a similar structure is the electricity markets throughout the world, where you usually have some kind of energy market and you have system services market or ancillary services markets. And this is the case also here. I will go into that a little bit more in detail, why they are different and their characteristics. Let's see now. But first, a little bit of picture of how this operates. This is a picture of the, you can say, the chain of information. If you look to the far left in this picture, you have the owner of different kind of physical assets that might exist in the system. It could be buildings, it could be local production of solar PVs, it could be battery storages or thermal storages, or it could be a combination of these things. We call these different kind of physical assets as market participants. They are the one participating on the market, but they're not doing that by their own. Instead, we use an intermediate agent, a software agent, acting on behalf of these physical assets, and the agent is the one that takes, you can say, the information from the buildings or PVs or what it might be, process that information, and decides on how to bid on the market, which is located to the far right in this picture. So the marketplace is on the far right, and there's an interface between the agent and the marketplace defining how these bids should look like. And so it's you can say a definition on how the bids should look like and what kind of relations these bids might have. This software agents has two different things, or 2 different communications, you can say. It's first with the physical assets that is representing on the market. That means that you need to have some communication regarding the state of the physical assets. It might be the state of the building or the state of the battery or whatever it might be that is the physical assets behind it. It also needs to be able to somehow send some kind of control signal to this and how to act, depending on what will happen on the market. And the other end, on the right-hand side of the agent, this picture, the agent decides based on the state of this building or solar PV or battery or whatever it might be, how it should bid to the market. And depending on what kind of physical asset you have in the background, this process is more or less complex. For example, if you have a solar PV as a physical asset behind the agent, the decision problem for the agent is mainly to make a forecast of how will the solar PV production be the next coming time periods. And that will constitute your bids to a market because that's what you have to offer. Now that might be complex in itself, but it becomes even more complex if you look at, for example, of a building that has the potential to move load between different points of time. That means executing demand response, because then you need to both assess the flexibility that exists in the buildings, and you also need to assess how you should use this kind of flexibility when you bid into the market. So the software agent are different depending on what kind of physical asset that you have in the background of the software agent, and those are also developed, a number of these agents within the FED project. As indicated in the previous picture, there are not one physical asset or one agent in the system, and I think Claes mentioned something about that we had 45 different buildings or market participants in the system. And so there are lots of these agents, and they can, as I said, be operating on different premises or in different kind of methods. They are not similar. It depends on what kind of physical asset they are representing. And in this picture, many of these are in the local system, but there might also be agents as the ones that's indicated now in the picture, which represent external actors. For example, you might have a producer of electricity or a retailer of electricity that could supply the local system with energy. And then that retailer is also represented by an agent in this FED marketplace. And there might be more than one retailer. They might be different for different energy carriers, might be one for heating, one for cooling, one for electricity, etc. So, but they all meet in this marketplace. The marketplace in the middle doesn't really know anything about what the physical assets outside the agents, what those are. The marketplace itself knows what kind of bids, knows the bids that the agents submit to the marketplace, and based on that information, it makes a clearing decision. Now, looking at the specific part concerning the energy exchange on this market, there are some main characteristics. One of the most important one is the integrated market for electricity, heating, and cooling. The integrated approach here is very, very important, and it's I think is one of the really top, innovative parts of the FED project. The bids from the agents, they consist of a quantity and evaluation. That means that you could say that I would like to buy this amount of energy for this price, for example. Or if you're not price sensitive at all, you can say that you need to buy this amount of energy regardless of the price. It could also be other way around, that you have some energy to sell for a minimum price, for example. So it consists of a quantity and evaluation, very similar to how trading looks like at traditional electricity markets. But this is also for each individual energy carrier. Now, there are something concerning the flexibility here that is quite important to capture, and we have built in functionality that we call bid dependencies in this market, and that is to facilitate different kind of flexibility options. One such option could be that you have a building which is can use a heat pump or can use district heating for heating purposes. What you can do in that case is that you can switch between these two energy carriers. And the market facilitates that market behavior by offering the possibility to say that I have one bid for electricity and one bid for district heating, and one of them should be accepted, but not both of them. So the market might then operate and do the clearing to see what is the most beneficial of accepting the district heating bid or the electricity bid. So in that way, it makes it easier for the actors to provide flexibility to the system. They do not have to make a decision on what to use, district heating or electricity, directly themselves, but they can get support from the marketplace to do that decision. This is also the case for demand response, for example. Let's say that you need a specific amount of energy, but you don't know but it's not important for you as a building owner, for example, exactly at what point of time you will use it. Then you can say that I will need this amount of energy. I place all of these bids covering the whole time period, but you let the market decide on when your consumption should be in order to make it as beneficial as possible. So that's a very important aspect of this market. There might be some kind of congestion or local infrastructure limitations available in the local system, and that is included in the marketplace. So the market takes care of that you do not exceed any transfer capacities within the local system. If you like mathematics, you can say that this is an optimization-based clearing. That means that all of this can be formulated mathematically. And while from an operational point of view, that might not be that important, but it's important to make it robust. If you can state these things in a concise mathematical manner, you get some benefits in terms of robustness of the market and how it's operated. The pricing mechanism, the market does not only deliver, you can say, what bids that has been accepted, but also the prices on the market. And the prices are dependent on the geographical location and energy carrier in the system. That means that you have lots of different prices available in the system, specifically if you have a congestion problem in the system that you cannot transfer as much capacity as you might like. But that also gives incentives for the actors in the local system to actually build production capacity or to execute demand response in places in the system where it's most beneficial to do so. So it creates incentives for that kind of investments and activities. Looking at the prices, it's a generalization or more complex. This is the basics of how the pricing actually works. It's aggregating different kind of supply bids and demand bids, and then you calculate the price cross. This is you can say basic microeconomic theory that you can find in any book on microeconomics, and this forms the basis. But putting into the grid infrastructure and limitations in that infrastructure make this and the different energy carriers make this a little bit more complex, but the basics is still there. So it's based upon well-known economic theories and how energy markets in general actually work. If we go to the system service market, it has some differences compared to the energy market. And first of all, it's under development. So even though the energy market is quite well defined by now, the system service market is not as well defined. This is tailored towards specific technical issues or problems in the different energy carrier systems. It might be that you need to resolve voltage problems in the electric power system or some temperature issues on the district heating system. And so it's targeting the owners of these infrastructures. And that is a different thing than exchange of energy between actors in the local system. So therefore, we have used a specific system for the system service market and system services. It's also operated on a, you can say, shorter time periods and finer time granularity, and that has to do with that this time of system services, which are very much technically oriented, typically needs to be executed on a finer time granularity and on a shorter time spans. So it operates in a different kind of time domain than the energy market. It's not as it does not have centralized clearing as the energy market has. It's more on a pay-as-bid structure, and it does not, since it's considering specific technical needs of the different energy carrier systems. It does not as integrated between this system because the technical needs are very different. But it might be that one service targeting one specific system might have an impact on another one. if we go back to the switching options between district heating and electricity, it might be that from system services perspective, you need to lower the electricity peak or consumption in the system. And in that might be one way of doing that is to switch from using a heat pump to use district heating instead, for example, in the system. But then you will all need to make sure that you do not incur any specific problems for the district heating system when you call upon the service for resolving an issue on the electric power system. You don't want to move a problem from one system just to causing another problem in another system. So there are these checks about this, but apart from that, it's not an integrated market. So just to summarize a little bit of what I've been saying now, we choose a market-oriented approach for the coordination purposes in the FED system to combine the coordination functionality and replication potential. That is one of the main arguments for why choosing the approach that we have chosen. Now, it provides functionality for small-scale actors to provide flexibility, which is very important in order to make this work. And it considers multiple energy carriers simultaneously in order to be able to use the benefits of, for example, switching or other synergies that might occur. And it facilitates energy exchange as well as provision of system services to the market through different kind of market mechanisms. And I think that's it. I'm happy to answer any questions you might have later on in this webinar. Thank you.
Thank you very much, Magnus, for this presentation. It was really good to hear all about it and what you had done so far. Now I will introduce, open up here. Now I would like to introduce our last speaker, and that is Joakim Pontén. Joakim is working as Senior IoT Solution Architect at Ericsson. And Joakim will give us a view of the digital platform that you are developing for the FED project. So please, Joakim, the floor is yours.
Yeah, hello everyone. Thank you for the introduction, Irene. Yeah, that should be it. Yeah, as Irene said, I work at Ericsson, one of the biggest telecom vendors in the world. I work at the business area of technology and emerging business within the IoT division. And what we're doing is we're building a technology and solutions to connect basically anything that is not a handset or a PC or something that you consider a personal device. So we connect basically everything from TVs and farms and industry robots and all that kinds of stuff, and also utility-related machinery. So in this project, we got the honor of implementing the ideas that Magnus presented in the last presentation to build the entire ICT solution that is to facilitate the connectivity and trading within the FED platform. So looking at if we look at the solution, we had a number of challenges, and that was first, I was just get everything up and running within the time frame of this project. A lot of the stuff has never been done before, but also to facilitate the replication of a future implementation of this, so we don't build a sort of one-shot solution. We want individual parts to be reusable and the overall solution to be reusable in the future as well. And looking at the current slide, we have this sort of three-layered information technology stack, which in the bottom you have the actual physical infrastructure, which in this case consists of the grid itself. We have a district heating grid, a district cooling grid, and an electricity grid. We have a number of consumers. I think we have around 35 different houses, for example, that consumes these different energy carriers, and also represents a lot of the flexibility in terms of the consumption within the solution. And we also have a number of producers as well. At the CHALMERS area, they have a power central which produces a lot of district heating and also electricity and cooling. There's solar panels, heat pumps, energy storages, all this stuff that we need to connect. On the top level, top layer, we have the actual Fed marketplace where the trading of energy and system services happens, and we have this agent concept that Magnus was talking about, where you have an agent representing a building. The sort of first challenge here was to how do we, in a good and future-proof way, connect a house to an agent that is not specifically a one-shot binding between a specific kind of building with a specific control system and this agent. We needed a generic way to do that, and in order to accomplish that, we used the Ericsson IoT accelerator from which enables you to basically connect anything. In that sense, you can connect the sensors directly, or you can interact with existing control systems, and you can expose all that connectivity in a generic way to overlying assets. So a lot of work has gone into how do we connect buildings and these grids and all the different stuff at CHALMERS, which is they have a big set of both legacy and new products, which have different protocols and ways of communicating. So that is sort of the southbound connection that has been done into the IoT accelerator. And by doing that, we enable to have one common interface for all the different agents to communicate to the different assets beneath without actually having to know the specifics about these devices. The IoT accelerator also enables us to keep track of historical data and to do monetization. In this case, we primarily use it to keep track of the actual energy transactions and the system services transaction that happens in the market. Once everything is connected, you have the next challenge, and that is to build the Fed energy market and the system service market, which facilitates the trading, and to build these agents that represents each building. And since we do bidding ahead of time, so one of the things that we needed to solve is how do we, for each of these individual and unique assets that we have underneath, how do we predict consumption and production for this? Especially the consumption of office buildings is fairly irregular, and it has a lot of patterns that are not that easily defined. So we stuck with using machine learning in the software agents that represent the different houses. So we take the historical data sets that the consumption of a house represents for district heating, electricity, and cooling, and we train these agents to predict the future. Basically, how much will this house consume in 10 hours from now? We need to know that in order to make to feed the market with the bids into the future, so it can make the dispatch decisions to make a good use of energy. It needs to decide when when should I execute any flexibility that we have in the underlying assets. And the control function also from the agent, once it actually gets a cleared bid to execute something, also takes place through the IoT accelerator platform, which enables you to send control signals in a generic way to an underlying asset. In the next slide, we have something very similar to what Magnus showed, where you have something, a house or production facility, which is supposed to be represented on the market by this software agent. And we also talk about a low threshold of getting into the market, and that means there is no real estate owner that programs their own software agent as a hobby. It's a bit too advanced for that. So yet again, the machine learning process of having an agent that can dynamically understand the underlying assets is very important, because then a company such as Ericsson can build one type of agent and can automatically adjust to the underlying assets consumption and production patterns, and also learn about how to execute the flexibility of that resource. So if you have a house, for example, you have typically you have the comfort span of the house within the indoor temperature spanning across 1 to 2 degrees, which you have to play with. And by increasing or decreasing the energy, the district heating intake, or the electricity intake for a heat pump, for example, you can adjust the energy consumption of the building and try to match that with the pricing of the market. And we needed to do this in such a generic way that we can reuse these agents for a bunch of different buildings. And I'm quite glad to say that we're very close to succeeding with that. And that means that onboarding new market participants will have a fairly low threshold in terms of investment. Another part that is important here is that the solution should be able to be replicated and also expanded in terms of the size of the market and the number of participants. And it basically should be able to represent a small area or a very large one. And that meant we needed to have an infrastructure that we could scale. And today that means running it in the cloud. So we build a cloud native solution that it's basically elastic in the terms of scaling for performance. So whenever the market grows, we can just add more resources to it and it will keep running. So in theory, we should be able to serve anything between 100 participants and several thousands without actually having to recode anything. We just need to add additional resources in terms of cloud infrastructure to the marketplace in order to facilitate a growing platform. Another very important concept of having the software agent solution in the cloud is that you have a real estate owner that is very good at managing the house, but does not have perhaps the deep understanding you needed to understand the inner workings of an AI agent working in the cloud. So what we have made an interface for the real estate owner to put in the constraints of the software agent. What can it do? What will it be able to do on this market? Which resources can it control and what should it represent? And being able to do that with a fairly simple set of basic constraints, saying, okay, this is the allowed indoor temperature and you're allowed to execute this sort of functionality between these hours. and giving them the ability to change that whenever they want. They can feel feel comfortable in allowing the cloud software to control their physical assets, because they can at any time change what is offered to the market, and the market will continuously run. So that's another important thing for us. Overall, it's for Ericsson, it's a much of a learning exercise. We could reuse a lot of different things that we had already in place from the IoT accelerator, but in terms of the marketplace, it's sort of a world first for a lot of the different functionalities in there. So there's been a lot of custom development done within the Fed project to make this happen. It's also important to note here that the marketplace runs completely autonomous. So you don't need any continuous manual operation of the marketplace. The agent and the market and everything, it runs autonomously from any end user interaction. So basically, as a user of the system, whenever it works, you really don't notice anything. The indoor climate of your house and the production facilities will continue to run as usual, but the energy pattern will match the supply of the market. So that is a short presentation of the ICT platform. If you want to know more about it, I'm happy to share. I try to keep it on a fairly high level. So thank you, everyone.
Thank you. Thank you very much, Joachim, and also Magnus and Claes for your presentations. It has been very pedagogic, and I really appreciate your presentation. So thank you very much for that. Now we are going to the last part of this session, and that's questions and answers and maybe discussions also. And we are happy to have your questions. To my understanding, I look into the chat box. I can't see any questions yet. Maybe you can start. Are there any questions? We are happy to try to answer them. I can also see from the participant list that we have a couple of representatives from cities in Europe, Dublin, as to my understanding, and also a person from Aalborg in Denmark. We have Antwerpen city with us as well, and Potsdam, and some other people as well. So maybe from the cities you may have any questions you would like to take the opportunity and ask the experts here around me. Okay, then I'll start with, maybe I can start with the first question then. And I will ask Claes. And the time for preparing this project application was very short. We have just 3 months to do the job and sent in before the deadline. How we was successful. We were among the winners. So how did we do? How did we put together this winning partnership, I would say, and also this very innovative project in such a short time? What was the challenges, and could you say something about that? That would be maybe of interest for the audience.
Of course I can, and I mentioned it also a little bit in my presentation that when we found this call, I think it was actually Johannesburg Science Park watching these kind of calls that could help to do what we were interested of here. But we had already large discussions before, perhaps not exactly on the specified topic, but as I mentioned, there was a partnership in a way already ongoing between RISE, CHALMERS, and the rest of Gothenburg Energy and so on. I think it was Ericsson who hooked on at the latest in the application phase. But we also have a very good help from a company here called IMCG in Gothenburg, also known in Celsius because they wrote the Celsius application once. So they had experience in this, and they help us to finalize the application with success.
Okay, thank you very much. And we can also say the partners in the project know each other very well from other cooperation that we have in other projects. So that was also easy to put together the partnership. Another challenge, I would say, and I will also address Claes again a second time, you coming from the big power supply company, Gothenburg Energy. If the FED project is successful, it means that we will buy less energy from the power supply companies. How do we look into new business models? How do they see their contribution in this project, do you believe? If you put on that hat.
Yeah, that is one role, of course, that if I think is a larger problem from that perspective for the big utilities like the electrical supplies in Europe, more than for a small, I mean relative small, like Gothenburg Energy, which is a utility company owned by the city of Gothenburg and only working in the city. But hopefully they can also gain quite a lot from this because they can reduce their cost. They have the expensive to run these fossil peaks, and hopefully they can sell the energy that they will sell will be of higher quality, less environmental impact, things like that. But of course, it is a situation. I think it's quite hard to deal with in a way for utility companies if they not own the whole system. But I think it's a big thing in this project to find the role of a utility company in these aspects.
And that is also a big part of the project, to find new business models and
also to work together with the customer to find a way to find the solutions. And that's why in this case Gothenburg Energy works together with their customers in a way, and also to explore the possibilities of digitalization for utility companies more, like to work together with Ericsson here and to learn from them what's the possibilities.
Still, there are no questions to my understanding. Then I can put another question to Magnus during time. This is an innovative project, and that was also important when we were writing the application, that what we would like to test here has never been tested before. And to look at the energy systems with all three carrier, electricity, district heating and cooling, that is new. Magnus, what was the biggest challenge for you and the RISE people when you went into this project? What do you see as the most challenging part of this project?
Well, I think it's one of the more challenging projects, not only for us, but for the project and the consortium as a whole, is to find a reasonable solution on how to operate and design this market, to make it say sufficiently functionality to be able to coordinate the you can say the use of the internal resources, of the existing resources, while being not too complex in order to make it implementable. So there's a trade-off there between these two things, and to make an overall understanding for what the market should do and shouldn't do. That has certainly been a challenge in the project as a whole, I would say.
Okay.
And also from our part, it's been a very, very interesting and but also a very challenging process.
Thank you very much, Magnus. Now, during time, we have the first question come in here from Greater Copenhagen Questions to Joachim Pontén. Joachim, I read the question here. You said that the accelerator cloud solution works autonomously, but I assume some kind of system support or monitoring is required to ensure, for example, security of supply. Joachim,
Yes. Yeah.
That's for you.
Yeah. Okay. Yeah. The IoT accelerator itself runs as a system as a service, a SaaS platform, which is managed by Ericsson, and we offer the system level agreements for the SLAs for the runtime of it and manages its operations. The Fed marketplace that runs on top of it runs autonomously, but we have a lot of monitoring tools that raises alarms whenever something is not working as intended. Given it's a fairly new solution, we expect that there will be a couple of alarms raised every now and then of course you need a support organization to take care of it. But the goal is to basically, you should not have to have a continuous manual monitoring of the system. Rather, we have an alarm-driven operation of it. So there are a number of alarms whenever something stops working that gets sent through different channels. So that we can work. We can go in and do manual work only when needed, and that is something I think is very important in terms of keeping the operation cost of such a system to a minimum.
Okay, thank you very much. I hope the Copenhagen is happy with the answer. Otherwise, you have to come up with a new question, maybe. Yes. There are no other question for time being. Maybe we can take one last question from our side here to discuss a little bit. We use the campus area as a test bed. And that is one, because here we can try solutions that is not possible to try in other parts of the city. We can buy and sell electricity in a way that is not possible outside the campus area. If this will be successful and be replicated in other parts of the cities, we need to do some lobbying job, perhaps. And that is also a part of the project. Could you say a little bit more, Claes, what we are going to do to look into barriers and drivers and also lobbying activities that could be needed for replication and dissemination?
Yes, and some of the job has already been done as well, but it's a little bit complex also to say what exactly do you mean, what we want to replicate here, and what can we do that Fed can do and that's not able to do without Fed. Mm-hmm. So we aim to take a closer look at this now in the project for replication, and to try to, what if we replicate it in another area of Gothenburg, what is possible to do, and what are the aspects of this, and also to compare it with the, let's say, the clean energy package of EU that is discussed there, and we have workshops like this with the energy agency here as another actors to see more closely to this. But the plan is to quite soon to produce, it's a deliverable in the project to describe it like 5 policies that we see that this we should address. Let's say one could be that we see the benefit of interacting between district heating and cooling and electricity could be something to lobby for, let's say, similar to how Celsius lobbied for district heating overall. And also perhaps on these matters, we also have some different views on other topics within the projects. So it's interesting also to see this, but it's planned to investigate this further during this year. Or perhaps Magnus will add something to this from his aspects.
also regulation and have an overview of the regulation would be necessary, I
Yes,
suppose.
of course.
And that is also a
so
discussion
regulation
high on the
on,
agenda. We know that.
on the electrical grids, and of course there are ongoing discussion with the EU what you want to do with this. But we have the system. The university area, as you mentioned here, is free of concession here for electricity, so we can try new business models. And we have this unbundling situation in electricity that you must take care of if you so you don't interfere too much with the electrical grid company and the trading of electricity and so on. But yeah, questions like that.
Very good. Thank you, Claes. Now we have a couple of more questions here. First of all, Sanna Gryner from Greater Copenhagen Utilities, she wants to say thank you. And also she forgot to tell her name. So now we have that. There is another from Greater Copenhagen Utility to Joachim again. Has IP rights been an issue?
Intellectual property is it's a big business for Ericsson. So most definitely, it's important to us. But the intellectual property right has been taken care of in this project by the partner agreement that we have between different parties. So once that was in place, we didn't have a problem with it. In terms of the solution that we're building, most of the stuff that is custom built is based on open source software. So that is is not a problem in that sense. So no, not really, not a problem. As we got the partner agreement in place before we're starting development.
Okay, thank you, Joachim. Now we have another question from Sanna K. Ko. I'm sorry if I'm not pronounced the name in correct way. The question is, isn't that some sort of a threat or a risk for a utility or energy company to share data information from utility companies to platforms so that the AI agents can use the valuable information? How to avoid security risks when sharing the valuable data? I suppose that is also a question for you, Joachim, or yeah, I believe Joachim or maybe Magnus. Magnus maybe also.
Yeah, I can just start. In the demonstration, there's no, there isn't an issue because we, as all the partners are, all the data connected to the system comes from the parties, and we have an NDA regulating what data we can share and not. So that's not a problem. Looking into the future, if you have such a data, that is, I cannot answer that. Perhaps Magnus can have any input to it. Otherwise, I think it's a utility company that needs to answer it.
Magnus, do you all like to add something or?
No, I don't think I like. No, not really. I think it's a matter of letting the utility companies answer that. To what extent there's a threat of using, for example, data that they provide. In this case, it's not. In the case for the demonstration here, I cannot really see that it will become a problem. It might be an issue if you replicate or scale up these kind of solutions.
I can give a comment because we have one question of this in the project. It's depending. Let's say that you use an hourly-based pricing on district heating. That means in a way that you will share the information exactly how you will operate. If the marginal price is based directly on the marginal production, let's say, then you can quite easily calculate this. And this is a security aspect that's not possible to share in a way, at least today in Gothenburg. So when looking at to create an hourly-based district heating price, we can't just take directly the marginal production cost, but we need to perhaps adapt it to the weather and so on. Actually, Gothenburg Energy is looking how we in the project can create that price model to avoid the secure aspects there. So things like that that you need to look on.
Oh, it's ongoing on
yeah.
the topic on our agenda. Okay, thank you so much so far. Here we have a new question, and that is from Michael Free-Move from TU Delft. And your question is, do you expect problems scaling systems like these up to a national scale? Yeah, what can we say, Claes? We have to work with regulation and adapt the regulation so it can be scaled up.
I think we will actually, at least when we look at replication, to stay in a district level in one way or another, not on a national level. Perhaps on these ones, it's. I mean, let's speak of district energy, district heating. So the district system, district heating system of Gothenburg might be one boundary for this. I mean, to have a natural island in a sense.
Yes.
Otherwise, small things like this, but it's something that we need to look more closer into. But on a national scale, we do not evaluate here.
But we have one of our partners is Akademiska Hus, who is a property owner of all the university buildings in Sweden, and they will could be a possibility that they could try the Fed solution in other cities.
Yeah, yes, of course, in other campuses.
In other campus, but still in the campus. Size, yes. Yeah. There is regulation issues that has to be handled. With
perhaps Magnus, will you comment on that?
Yeah, yes, I can do that a little bit. I think that, as you say, there might be some issues. Of course, there are issues concerning regulation and so on. On the comment on that is that, I mean, this is our continuous discussions on this right now. I mean, the EU points out local energy communities and system as one of the possibilities to enhance to increase the amount of renewables and create a sustainable energy system in Europe. So in a way, perhaps regulations need to be adapted to facilitate that kind of development. And another comment from my side is that if you're looking at replicating these kind of solutions on a large scale in a national level and so on, it becomes very important that you set up the systems so that you will increase, or you will not at least decrease, the overall resource efficiency of the system as a whole. If all of these different small islands sub-optimize their own kind of benefit, then it might not always lead to a benefit for the system as a whole. But depending on how you design the markets on the local scale and the systems on a local level, you might address those kind of inefficiency more efficiently. So there's an important to have that in mind as well, so we don't sub-optimize our energy system on a national level to reach local goals only.
Okay, thank you very much, Magnus, for the answer, and I hope everybody is happy to what you have been presented here. Time is running out, so I would like to thank you for attending the meeting, and also I would like to thank our speakers for your participation. And as I said, we are halfway through the project, so much more will be possible to discuss with you later on if you are interested. So take next picture. Click at that. So thank you to you all, and if you have any additional questions, you are free to address us directly to the Fed project, and we will be happy to start a discussion with you. So thank you very much. Bye bye.